All right, here's our second optimization problem. So this one just says the product of two positive numbers is 288. Find the two numbers so that the sum of twice the first plus the second is as small as possible. So when we see as small as possible, that tells us we're looking for a minimum, and which also tells us we're doing optimization, right? Because optimization is saying, given all of this information, find the minimum or the maximum value for a function, okay? And so this one, we're looking for a minimum. And this one would be something you could use in like business. So there are businesses that say like they have two different costs, and you know they want them to multiply to 288, and they're trying to minimize those costs as much as possible. This could be something like you're talking about area, right? You need to make a corral that's 288 square feet, and in this case we have twice the first plus the second, so that one wouldn't quite be a perimeter. But it's the same concept, right? We would say, like, if this is the area that I need is 288, what are the smallest possible numbers that I can make that fence that I would get a perimeter that would still give me an area of 288. So this is actually like real application for calculus. I know it's kind of hard to see now, but there's just so many applications where people want to minimize, I almost said minimize profit, but maximize profit, minimize expense, maximize area, minimize materials. And then we're constantly looking at maximizing and minimizing things, and this is a real application for that. So let's look at this one. So remember, when we're doing optimization problems, we kind of have a pattern that we follow. So the first step of this pattern is that we choose our variables and draw a labeled figure. So this says that we have two positive numbers. So I need to label each of those with a variable. So my first number is going to be x. And then my second number is going to be y. Okay? Now, since this isn't like cows in a corral, this isn't a box, we don't need to draw a labeled figure because there isn't a figure to draw because we're not talking about anything geometry here. But that would, if you had an actual, like a real world application, you would draw a figure so that you can really understand what you're looking at. So then the second step is to write a primary equation and to isolate whatever needs to be minimized or maximized. Okay, so this says we want to minimize the sum of the two numbers, right? The sum of twice the first plus the second. So if we wrote that as an equation, this is going to be our primary equation. Remember, our primary equation is the one that we want to minimize or maximize. So it's whatever we're trying to minimize. If we're trying to minimize volume, then our volume equation would be our primary equation. If we were trying to maximize perimeter, our perimeter equation would be our primary. So it's whatever we're trying to minimize or maximize. It's the thing we're actually trying to optimize. So our primary equation is that the sum, we're trying to minimize the sum of these two numbers. And I should really not write an equal sign there. I should write, I should just do like a little arrow. You just don't want to like run on equals everywhere. Okay, so the sum of these two numbers of 2 times the first number plus the second number, we want to minimize the sum. So we're trying to minimize x, right? We're trying to minimize, when we add these two numbers together, we're trying to minimize that answer, okay? And then isolate whatever needs to be minimized or maximized. In this case, it's already isolated because it's that answer, right? This is what we're trying to minimize, the answer when we add the two together. So step number 3 is that we rewrite with only one variable on each side. And this may require a secondary equation. And almost always it's going to require a secondary equation. So what is our secondary equation? How else do we know that x and y are related to each other? You know, so we look at this and it says the product of the two numbers is 288. So those are related to each other, that when I multiply the two of them together, that I'm going to get 288. So that's my secondary equation. And then I use the secondary equation. Remember, basically the short of optimization is make two equations, plug one equation into the other, find the derivative and solve. Okay, and that's like a super simplified way of thinking it, but that's basically what we're doing. Make two equations, plug one into the other, find the derivative and solve. Okay, so we've made two equations. Now we need to plug one of them into the other. Our secondary equation is going to plug into our primary equation so that we have our primary equation in terms of one variable. It only needs to have one variable because we're trying to optimize it, and we can only take the derivative of one variable in optimization stuff. So let's get our secondary equation so that it's in terms of like either x or y is all by itself. And in this case, I think we're going to do y by itself because it's just easier, then we don't have to multiply by 2. So we have y equals 288 divided by x. So then we plug that into our primary equation for y. So we're going to plug it in. S equals 2x plus 288 over x. Now we have our actual equation we can optimize, okay? We can't optimize things until we have one variable on each side and only one variable on each side. And then we need to figure out, like, our primary equation is what we're optimizing, right? We're optimizing a sum. We're trying to minimize the sum. So our fourth step is to write the domain. So what's the domain of our function? Well, we have an x in the denominator, which means we definitely can't divide by 0. So we know x can't be equal to 0. We know that. And then we look back to our question to ask what the domain is, what our constraints are, because again, we live in the real world and most optimization problems are real world application. So we have to decide, like, what does the real world tell us that we can and can't do? And in this case, it just told us the two numbers can't be negative. They have to be positive. Because, I mean, in theory, you could multiply two negative numbers together and get 288. So in theory, there are numbers that exist, but our constraints say, nope, we don't want the negative ones. We only want the positive ones. So our domain is actually x is greater than 0, right? Because not only can x not be equal to 0, it can't be less than 0 either. It has to be greater than 0. So that's our domain. And then our fifth step, remember, we find two equations. We sub one equation into the other. Then we find the derivative, set it equal to 0, and solve. Okay? So our final step, number 5, is that we find the derivative of the equation we're trying to optimize, the function we're trying to optimize. We set it equal to 0 and we solve. So let's derive this. So we get s prime equals 2 plus, now remember that this is really 2x plus 288 times x to the negative 1. So when we rewrite that, we're actually going to have, when we derive it, we get minus 288 x to the negative 2. And we can rewrite that. It doesn't really matter at this point, but it might be easier to see. It's 288 over x squared. So that's our derivative, right? And this is what we're trying to use to find the minimum or maximum of our original function. We have to set this equal to 0 because minimums and maximums of functions only exist when their derivative is equal to 0. And then again, minimums and maximums of functions only exist when the derivative equals 0 or is undefined. So we have to find these critical numbers to find a minimum or a maximum of that function. Okay? So now let's solve for x. We are going to go ahead and subtract 2 from both sides. And then we're going to multiply both sides by x squared. Then we're going to divide both sides by negative 2. And we get x squared equals 144, which is good. It needs to be positive, right? And then we take the square root of both sides, and we get x equals plus or minus 12. So our options for minimums and maximums in this function are plus or minus 12. But again, what are our constraints? Our constraints said that x has to be bigger than 0. It cannot be less than 0. Okay? So our negative 12 is just not even an option, right? Our only option is x equals 12. So here's our only option is x equals 12, and then we just check. More often than not, if you get the number, it's probably going to be a min or a max. We should probably check. So let's check. If I plug in something smaller than 12, like not negative 1, 1 to my function, what do I get? Well, I get 2 minus 288 over 1, which is a negative number, so it's negative. And if I plug in a number bigger than that, like 13, I actually end up with a positive number because 288 divided by 13 squared is less than 2, so it ends up being positive. So I know that my function is doing this action, right? It's decreasing, 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 and then increasing. So 12 is a minimum, which means numbers, when x is less than 12, you know, like over here, these numbers produce a larger sum, and then we're getting smaller sum, smaller sum, smaller sum, smaller sum, smaller sum, and this is the smallest possible sum that we can get. And then as x gets bigger, we have a bigger sum, bigger sum, bigger sum, bigger sum, bigger sum. Okay? And then our last step is to figure out what y is, right? Because we defined our variables. We're going to come all the way back up here and we're going to say, well, we already said what one variable is. Now we've got to find out the other variable. If x equals 12, what does y have to equal? Well, we only have one function that really relates those two together, and that one is, let me find it, x times y equals 288, right? That's the only one that tells us that only has x and y in it. Our primary equation doesn't. It has an s in it as well, so we can't really plug into that one. So x equals 12 times y equals 288. We divide by 12. And y equals 288 divided by 12, which is 24. So in this case, the two numbers we're looking for are 12 and 24, that when we multiply them together, they equal 288, but when we add twice 12 plus 24, we get the smallest possible value. So that is optimization. Yay!